Today I'm going to continue my series on weak interactions by talking about nuclear proton and neutron exchange that occurs within the nucleus. And this happens because we understand that a proton can interact with a neutron in a way that they switch places, that the neutron becomes a proton and the proton becomes a neutron. And this causes a Yukawa screening potential, it's called, that screens the electromagnetic repulsion between the protons and helps with the nuclear force, the strong nuclear force. So, in essence, the strong nuclear force, or this component of it, is due to a weak interaction, which is not something usually talked about when you're introduced to the strong force. Anyway, we have this interaction occurring. The first person to come up with the hypothesis about it was Yukawa. And if you read his original paper, he was just guessing. He was just guessing, oh, there must be a particle that is causing an exchange that causes the strong force. And that's because particle exchange theory was just getting popular. So that was developed into a whole big theory where a pion was discovered, and they said, oh, pions must be the particle exchange particle that gives us a strong interaction, and a theory was developed around that. And then Fermi and Yang, many years later, came up with the hypothesis, well, proton-antiproton pairs and neutron-antineutron pairs could also interact between protons and neutrons and cause these types of exchanges to occur. And then, of course, when the quark model developed, they said, oh, well, actually there has to be quarks there. They had gluons, and quarks and gluons are causing this exchange. And so if you go to Wikipedia now, you get the quark and gluon explanation, and they may give you a little bit of history on the Yukawa explanation, and maybe just a line or two about the Fermi-Yang one. Well, in truth, the weak interactions are due to quantum fluctuation interactions, electron-positron quantum fluctuations and proton-antiproton quantum fluctuations. And the way they happen simply is we have a neutron, which I just show as a proton and an electron inside a shell of quantum fluctuations. And that's because we know, due to scattering experiments with protons, that they have a shell of quantum fluctuations that we scatter off of at the charge radius. And that's something that's often skipped over when people are discussing the structure of a proton. And I just put protons and electrons because when you combine a proton and electron, you get a neutron, and then a neutron decays when the electron leaves the proton. So it's much simpler to just think of it as a proton electron and skip the quark theory. You can go back to it later if you really want, but it's not necessary. Anyway, you have a neutron and a proton, and in between you get an electron-positron quantum fluctuation, where the positron interacts with the electron-like component within the neutron, because it's inside the shell. And then you have an electron inside the shell of the proton, which converts this to a neutron. So you get a proton and a neutron when you originally had a neutron and a proton. And both of these interactions are typical. I talked about them on neutron production and neutron decay in two previous videos, and this just combines the two simultaneously, and it makes it look like protons and neutrons are trading places. And all you need to describe this is an electron-positron pair. You don't need anything fancy. And then you have, in this case, a neutron can interact with a proton-antiproton pair, where the proton component is annihilated with the antiproton. And so you have a proton that's ejected, and that gives you, there's an electron left, so you have a free electron, and your free electron has a proton next to it, then you can have another quantum electron-positron pair that annihilates with the electron, and then the electron becomes free inside the shell of the proton, converting it to a neutron. And so this is a two-step process, but you can have a process that starts with a proton-antiproton annihilation of the neutron, or conversion to a proton. And it's important to note that the spherical structure around an electron is at the Compton radius, which is much larger than the nucleus. And so because of the interference of the local protons and neutrons, when a bare electron is released inside the nucleus, it can't form its normal free particle structure. So a free electron within the nucleus is going to recombine with a proton rather rapidly, unless it has enough energy to be ejected and cause electron emission. And electron emission is discussed in the video I just finished. So we also have a couple basic interactions where particles appear to do quantum jumps, where a proton interacts with a proton-antiproton pair, and the antiproton annihilates with the proton, then the proton becomes free right next to it, and then it becomes stable, and it takes the energy of the original proton. And the same thing happens with a neutron, only a little bit different. You have a neutron with its proton component and electron component. If it simultaneously interacts with both an electron-positron and antiproton-proton pair, then it can appear to have a quantum jump, and a neutron will reform on the other side. Now note that this isn't a neutron-antineutron pair, because a neutron is not a fundamental particle. It's due to a combination of an electron and a proton. So neutrons do not naturally form quantum fluctuations. At least I don't think they do. I think when you have a quantum fluctuation neutron, you have this pairs that are occurring side by side, where you have the quantum fluctuation that's an electron-positron and a proton-antiproton, which behaves like a neutron-antineutron. Then it's important, going back to Yukawa, that Yukawa thought a pion was causing the proton-antiproton exchange, or proton-neutron exchange. But in reality, it's a electron-positron pair that's principally causing this exchange. Well, it turns out that a relativistic positronium resonance, which is made of an electron-positron orbiting at relativistic velocity, has the same energy as a neutral pion. So in effect, Yukawa's neutral pion model is really an electron-positron model, although it doesn't have to be relativistic to work. So Yukawa and people who interpreted his idea as a pion, it was sort of correct in that we had a electron-positron that's responsible for the interaction. And it's a true weak force, and only quantum fluctuations are required. You don't need W particles to convert quarks to electrons. If you consider that the bare electron is already in there, you don't need a conversion process. And so W bosons are unnecessary. And also neutrinos are unnecessary, because quantum fluctuations also act the way a neutrino should in weak interactions. So if we have quantum fluctuations that are triggering the interactions up front, then you don't have to have a neutrino involved. And so this is one way to simplify physics, and also it helps combine this component of the strong force with electroweak theory, because it's purely a weak interaction. And I'll talk about that a little bit more in the next video. Anyway, I hope you liked the video, and if you do, please like and share it with your physicist friends. And also, if you'd like to read about quantum field theory, I've linked to a couple papers below, and I have books on quantum field theory. The zero-point universe covers the basics of this, and my book on particle theory, the Goodbye Quarks, the Onium theory, goes into a little more detail and a little more up-to-date. And I also have the 100 Greatest Lies in Physics for your entertainment. Anyway, if you buy one of my books, I'm a retired independent researcher, and that helps me in my retirement and helps me produce more videos and do more research. And I also have a Patreon account. So thanks for watching.